factorize here. We need to do integration. So how are we going to integrate? Okay, so now we have there are different conventional or classical functions that we can use. And here are a few. So here I'm gonna just name 3 conventional ones, and these are permutation invariant. So we're going to see beautiful properties of graph neural networks, particularly GCNs, in the coming sessions. So like invariant, permutation invariance, and equivariance. And these operations, they are permutation. Remember the graph, when you change the order of the nodes, the graph topology remains the same. So these operations preserve those too. And here for the mean, so the mean basically is what we talked about. We can easily average. So we take the average of all nodes in the graph. So for each node in the graph, so for each node, this is, in graph, so the graph nodes, these are the graph nodes, okay? And we take the embedding, so this is the final embedding, and we simply, final embedding, and we simply average them. So we take the average. So here the HG is a simple average. Actually, here I should probably change the notation to make it consistent. So I just, let me take a note of that. So here we have HG. So we can put, here I'm going to fix these quickly. So it's better to have K because it's layer, it means like layer K. Actually, we can, I always like to kind of keep notations consistent as much as I can, avoiding typos, hopefully. So here we have graph G, KG, and then KG. Okay, so first we can use the mean. We can use also, this is called the global mean pooling, okay, in conventional deep learning. So we're just kind of doing the averaging. We have seen this also. This is a simple aggregation, right? So you're not just adding up, you're summing, but you're dividing by the number of nodes here, okay? So you're taking the mean. You can also take the max, and this is called max pooling, which means when you learn these representations, so why this is something that you can do. So let me give you the intuition here. So remember, when we have the sigmoid activation function, the activation function that we apply to our transformed and aggregated features, right? So after applying the activation function, we get the vector here. So this vector will only keep very high values, which means 0.8, lots of zeros, 0.7, 0.2 maybe, okay? But it will transform all negative values. Any value that you have here inside that is, for example, negative, it will be transformed, it will be mapped onto 0, because this is, this is the function. It maps all negative values. Okay, so if you have a 0 here, all negative values will be set to very close to 0. Okay, so so now in this case, what happens is that here you're going to have a high response. So you're going to have your H. So let me write it in this way. Okay, so imagine this is my HK. All right, so this is HK, and these are all the elements from. So I'm going to write them this way. So from element 1 to element dk. Okay, so these are all the dimensions. And I'm going to plot the values of between 0 and 1 using this activation function, for example. So we have 0 to 1 here. And if we plot the values, we're going to have maybe few values up, like something like this. And lots of zeros, maybe if we have negative data. So this is the response. This is the activation map of the embedding. This is the shape of the embedding that we have for each dimension. Now, imagine that you have many other shapes. So this, you will basically duplicate this. So this is following the activation. And you're going to have, for a particular, another node. So this is for maybe, So let's say this is for node I, and this is for node J. So this is HKI, and this is here HKJ, and we put the nodes like we do this notation, okay? So now let's do this differently. We're gonna see also different distributions. So we're gonna have maybe something like this. So different responses for different dimensions or different features. And what happens here is that actually in a neural network, remember guys, in a neural network, we want to only have, we want to have features that are activated, that gives, a strong response, right? So the idea of taking the max over this, so you can take each feature right here, okay? And you take the maximum value. So the maximum value here, so if we were going to build the graph feature map, so the final graph feature map, the average, the maximum here, so this is the graph, G. And for the first, what we can do, so we take the maximum of each value. So we're going to create an embedding for this graph, HK for graph G, and we take the maximum value. So the maximum value here would be this guy. So we're going to put that here. And then for the second one, very high responses. The third one, so maybe the third one would be here, so that's higher. So you can see that we're getting a lot of high responses, the maximum responses that we got. And the idea here is that, well, taking max pooling, when you want to activate, you actually want your neurons to have large activation, okay, for some important features. So you want the most important features to have very high activation because they have high values, all right? So here, when we take the max, if you see that feature has been activated, that dimension D here is equal to 2 has been activated in one of the nodes, then you consider it as important and you say, well, I need to keep that information because this, feature in that particular, this feature 2 in my embedding in the final space of my node J is highly activated, which means it is actually important. It has been activated, has a strong response. So to my original signal, to input, x0, which is the input feature. So it has a strong response to the input feature. So I will take that into consideration. So that's why, maximum will, it has been used in classical deep learning a lot. And here, one thing also is that if we want to take the average, we simply take these guys, the same DK, okay, and we average them. So that's the idea. We do the averaging here. And the averaging means that I don't want to focus on the maximum response or the strongest response. I want to see the average response of that particular dimension or feature across all my nodes. So these are completely different strategies, and each one of them has pros and cons and a particular rationale behind them, okay? So the third one is global sum pooling. So sum pooling here is taking simply the summation. So you add these up. So, and if you add them up and you're not getting the maximum, you're going to have even stronger value, because here, if we add these up and let's take, the graph, and we're going to add these two, okay? So you're going to have not only a response up to here, but it's going to be additive, right? Cumulative. So you're going to have really big responses along your graph, along your embedding space dimensions, okay? So this is the, 1, 2 decay embedding space dimension. So this will enhance without a normalization. And this will keep the strong signal, keep the strong activations and also dimensions. And this one is a normalizer. It normalizes. It's an average, activation at each embedding dimension across nodes. Okay. across the graph nodes. Good. So these are three different ways: global mean pooling, max pooling, and sum pooling. And however, these have several issues, all of them, and you can think about these issues. Actually, I would like you guys to kind of take pen and paper and try to think, what are actually the issues that may arise from collapsing all of these embeddings onto a single embedding using a max pooling or an average pooling? How does that kind of, where can this fail or lead to a bad representation of my graph, a bad embedding of my graph? So I'm going to give you one example here. So for example, so let's look at this. So before we go into the example, there is an important note. So global pooling over a graph, or especially particularly large graphs, it will lose information. You can see that we're losing a lot of information because we're collapsing all of these guys onto single value, right? So it's very reductionist. And it cannot differentiate between different graph structures. So let's see how these global pooling methods, max, mean, or sum, fail to differentiate between different graph topologies. And so let's try to find a case, for example, where two graphs, G1 and G2, have different embedding distributions. However, their sum, the summation of these, embeddings, right? It produces the same number, for example, 0. So take a minute and think about this. Let's try to come up with a bunch of embedding numbers where when you sum them, okay, across a graph. So let's say one single embedding, so one value, the dimension of the embedding is 1. So one-dimensional space. You take scalars, you add them up, and you get a 0 for G1, and different values or different scalars. And then you add them up, and then you get another 0 for G2. So which means the average embedding for G2 is actually 0 across its nodes, and the other one is 0, which means they are identical, which means they are very similar. But if you have different distribution of embeddings, the structure, the topology, the A of the graph, and the features, the original features and the topology of the graph, the adjacency matrix of the graph, should be different. Okay? So, for instance, we can look at this case. So we have, for example, here, these values. We have a negative missing here. So let me fix this also. So -1. And then do we have actually, so let's see if we have, so here, yeah, so this is, we have 0.1 and we have -0.6 and -0.5. Okay, so these two, this is, so these are actually add up to 0. So that's correct. So I was kind of misreading the comma here. There is a comma, so the separation is right here actually. Okay, so we have 4 numbers, and these 4 numbers, they do add up to 0. Okay, now let's see for a different sequence. So this is another sequence, and then this also adds up to 0. And you guys can see that these are completely 2 different embeddings. So this is the embedding of node 1, 2, 3, 4. So let's say you have 4 nodes in the graph here. You may have more, right? But when you add them up, you get 0. So this tells us that basically we cannot differentiate between G1 and G2 using this global sum pooling. All right. So this is one single issue. You can identify other issues. So there has been, this is an ongoing area of research, and there are several papers and several research directions where you can pool graphs. You can create, graph pooling techniques that allow us to kind of maintain the expressiveness of the graph and the topology of the graph. And these operations, ideally, they would be node, like permutation invariant. And here, this is an example, a simple example, which is hierarchical pooling. So hierarchical pooling has been proposed in 2018. It's a paper published in the advanced neural information processing systems. And here you can see in this NeurIPS paper, we have basically different, hierarchical way of pulling the graph. Okay, so we don't do one single step. So first, we will divide the graph into different clusters, and we will create the embedding of each subgraph individually while maintaining the connections between these clusters. Okay, so these edges that connect clusters. And then we're going to start collapsing. Basically, each graph here, each color will collapse onto a node. So let me explain that in a bit. So this allows for a better graph differentiation. And here is a toy example. So in this diff pool method, at each hierarchical layer, we run a GNN model to obtain embeddings of nodes. Okay, so this is what we have seen. So all of you can code this up. So up to this point, all of you should be able to code this up. So the mathematics, the mathematical formalization is clear. We can create node embeddings. Now, where to go from there? So after creating node embeddings, what we call them the HKI, right? For each node I in V. Now we then use the learned embeddings to cluster the nodes together. It's so cool, a very cool idea. So basically, these are the learned embeddings, and we use them to run a clustering algorithm. So we can easily cluster. So for example, here, if you use, k-means or any kind of clustering algorithm, you can cluster these nodes based on their embeddings. So after you cluster these nodes based on their embeddings, you're going to end up, you're going to have or produce multiple clusters or multiple subgraphs. Remember, so these are subgraphs. So for example, let's take the blue color. So this is a subgraph that has 4 nodes, okay? So 4 nodes in a cluster. Now, after that, they run what they call a GNN layer and the quiescent graph. So the quiescent graph is the graph where we have multiple, basically clusters. And here, what happens is that when you do a GNN layer here, so this is what we collapse all of these guys, okay, onto a single node. So this is, what we call the integration, the node embedding integration for this particular subgraph. So we take this subgraph, we can simply use, for example, max pooling or mean pooling or any of these operations, but now we're using them at the subgraph level. So we've broken down the graph topology into smaller topologies based on our clustering, and that will allow us to kind of, learn these layers, these mapping functions, and we will now get a node embedding right here for this particular, graph, right? So we'll have node embeddings, right? And then after that, we're going to do the same. So we will use these node embeddings we will collapse every single color matches here. So the yellow here is the yellow cluster, right? The blue is the blue cluster. You can see the color matches. The red is the red cluster, right? So this whole subgraph has been collapsed or mapped onto a single node with its integrated or pooled average embedding. And there are different ways of doing that. So you guys can read the paper and discover the way it has been implemented. But there are different ways. And once you do that, you repeat the clustering. So here you can see that this is the pooled network at level 1. So you do pooling here, as we explained earlier. And now you recluster again. So recluster the embeddings. So we have the pink embeddings, right, that we pooled and we do the clustering. So here we discover that we have only 2 clusters, and these 2 clusters will be mapped onto only 2 nodes in the next layer. So you can see here, all of these guys are mapped onto this node using, pooling. So now we end up with a single cluster, right, with only 2 nodes, and we do final max pooling or any type of pooling, and we can see that hierarchically, in a hierarchical way, we have beautifully and nicely transformed a large graph onto a single, a large graph with multiple embeddings onto a single node here and with a single embedding. And now we can easily pass this through an MLP, a graph classification network. So this, the W function that we talked about, or a multilinear function, right? If you have the W, you have biases like weights and biases. So this is, the classifier, the prediction hat here, okay? The prediction that we defined and with its hyperparameters, and we do the optimization, okay, using these hyperparameters, for example. But here, basically what we were able to do is to collapse the whole graph onto a single node with the final learned embedding. So this is H, final layer K, and of our graph G. All right. Cool. So please have a read at the paper. It's a very interesting paper, and it would be so nice to kind of look at the math and debunk the mathematical equations and understand exactly the different steps of diff pool and how it works. This could form a simple homework where you code this up from scratch, and you can compare this against simple pooling, all these pooling methods that directly pool the graphs globally without any multi-step approaches such as hierarchical pooling, and you can compare the ability of these approaches in differentiating graphs and classifying or regressing in terms of performance, but also in terms of distinguishing between different topologies. So the different things that we can explore using diff pool, and also variants of diff pool. All right, cool. So now the last part. Okay. So far we have seen in this lecture the GCN training paradigm, how to train and optimize GNN models in general. We also explored their powerful inductive capability, and we have seen different examples: a node-based, a node-level multi-regression model, and also a graph-level multi-regression model, so 2 supervised tasks. And we've seen also different approaches for transforming node embeddings into graph embeddings using different pooling methodologies, which have a few disadvantages, and how these were addressed using hierarchical pooling. And there are several new state-of-the-art methods that address this. But this is just a simple example that you should be able to understand and go over in detail.